Less than 300 million years after the Big Bang, the universe was not supposed to look busy. It was supposed to be young in a very literal sense, still gathering its first stable systems, still building the structures that would one day become large galaxies, clusters, and the long web of matter stretched across space. Yet when the James Webb Space Telescope began looking deep into that early era, some of the first reports carried an uncomfortable message. There were galaxies so bright, and in some interpretations so massive, that they seemed to arrive ahead of schedule. Not by a little, by enough to make astronomers stop and ask whether the timetable itself had been too optimistic. That tension did not begin as a vague impression. It began with one of Webb's main jobs. The telescope was built to look at infrared light, which matters because light from extremely distant galaxies has been stretched by cosmic expansion on its way to us. Objects that once shone in ultraviolet or visible wavelengths reach Webb shifted deep into the infrared. That is how a telescope launched in the 2020s can examine galaxies from the universe's first few 100 million years. Webb's large mirror, its cold operating temperature, and instruments such as NIRCam and NIRSpec make that possible. One of the clearest examples is JWST-140. Webb observations placed it at a redshift of about 14.3, corresponding to a time less than 300 million years after the Big Bang. That is not speculation. That distance was pinned down with spectroscopy, using the location of the Lyman break in the spectrum, which is far more secure than just estimating a distance from colors alone. In other words, the object's age is not mainly the controversial part. Its existence at that time is very hard to dismiss. A galaxy seen that early does not automatically break cosmology. The standard model, lambda cold dark matter, absolutely expects galaxies to form early. Small structures should collapse first, gas should fall into dark matter halos, cooling should allow stars to form, and over time mergers and fresh inflow should build larger systems. Nothing in the model says the early universe must be empty. The real issue is rate. How much structure can be assembled in under 300 million years, and how efficiently can gas be turned into stars? When some Webb candidates first appeared unusually bright, several teams argued that if the brightness truly reflected large stellar masses, then galaxy assembly might have proceeded faster than many pre-Webb models predicted. That was the source of the unease. Brightness, though, is where careful science has to slow down. Bright does not always mean massive in the simple, everyday sense. A galaxy can look extraordinarily luminous if it is forming stars at a fierce rate, if its stars are young and hot, if emission lines are boosting the observed flux in certain filters, or if dust and stellar population assumptions are being modeled imperfectly. This distinction matters because the earliest public reaction to Webb included some headlines that jumped too quickly from bright to impossibly huge. Later work showed that a number of early mass estimates were likely too large, or at least more uncertain than first presented. So the strongest version of the claim is not that Webb has already proven standard cosmology wrong. The stronger and more accurate statement is narrower. Webb has revealed a population of very early galaxies that are more luminous, more abundant, or more evolved than many astronomers expected from pre-launch modeling, and some of them still sit near the upper edge of what those models comfortably produce. That distinction between observation and interpretation is the heart of the story. The observation is that Webb is seeing galaxies at very high redshift, including some from the first few 100 million years. That is established. The interpretation is that some of these systems may have built stellar mass very rapidly, perhaps faster than many earlier simulations allowed for. That remains active scientific work, not a settled overthrow. The speculation is that the tension could eventually point to deeper revisions in how we model star formation, feedback, halo growth, or even the broader cosmological framework. That is still open. The telescope has applied pressure. It has not delivered a final verdict. To see why the pressure is real, it helps to picture what a young galaxy must actually do. It needs a dark matter halo to collapse from the tiny density variations left behind from the early universe. Ordinary matter then falls into that gravitational well. The gas must cool. Some of it must avoid being heated or blown back out by energetic stars and supernovae. Dense clouds must form. Those clouds must collapse into stars. Then enough of those stars must shine strongly enough, long enough, for Webb to see the combined light across billions of years of travel time. Every step costs time, and several of those steps can work against each other. Star formation creates radiation and stellar winds that can suppress further star formation. Supernovae stir and expel gas. Black holes can also inject energy. So when astronomers say certain galaxies seem too bright too early, they are really saying that the full chain from halo assembly to visible starlight may have run with striking efficiency. That is a physical statement, not just a dramatic one. There is also a historical layer to this that makes the moment easier to appreciate. Before Webb launched, much of our picture of the earliest galaxies came from the Hubble Space Telescope and from models tuned to the limited data available then. Hubble had already pushed very far into the young universe, but Webb was designed to go deeper in the infrared and with far greater sensitivity to faint early sources. Astronomers expected surprises. The only honest disagreement was about size. Would Webb mostly fill in missing details of a familiar story, or would it expose that the opening chapters had been too tidy? The answer, at least so far, seems to be somewhere in between. Webb is not tearing the book in half. It is rewriting several pages and marking many others with heavy notes in the margin. One reason this feels so intense is that the universe gives us very little time at high redshift. When we say less than 300 million years after the Big Bang, that is not just a big number made small by cosmic standards. It is a severe constraint. The Milky Way is more than 13 billion years old. Our Sun alone is about 4.5 billion years old. Entire chapters of galactic evolution that seem spacious in the nearby universe must be compressed into a tiny early interval when dealing with redshifts above 10. A system that looks unexpectedly luminous at that epoch is not merely old in an emotional sense. It is operating on a schedule that leaves little room for wasted motion. Some of the most provocative early Webb claims will continue to be revised because that is what good astronomy does. Spectroscopy will replace photometric guesses where possible. Better stellar population models will change inferred masses. Larger samples will reveal whether the brightest objects are rare outliers or signs of a broader pattern. Gravitational lensing studies, deeper surveys, and comparison with simulations will all sharpen the picture. In some cases, the tension may ease. In others, it may harden. That is not a weakness in the science. That is the science doing exactly what it should do when a more powerful instrument opens a new observational window. Webb did not merely find one odd object. It opened a wider view of cosmic dawn and found that the early universe may have been more efficient, more active, and in places more organized than many astronomers expected. JWST GSZ 140 is important not because it single-handedly breaks the model, but because it reminds us how quickly nature can exploit every available path to structure. A young universe did not mean a simple universe. It meant one where the race between gravity, gas physics, radiation, and time was already underway, and perhaps underway faster than we had drawn it on paper. So why did Webb find giant galaxies so early? The careful answer is that Webb found very early galaxies, some of them astonishingly bright, and our interpretation of several of those systems suggests growth rates that sit close to, and sometimes strain, the comfortable edge of standard expectations. Some of the tension may come from how we translate light into mass. Some may come from star formation in the early universe being more efficient than many models assumed. Some may come from feedback, dust, or black hole activity behaving differently than simplified pictures allowed. And some part of the tension may still fade as the data improve. But there is a harder possibility that cannot be dismissed yet. The early universe may not have been a slow and hesitant beginning. It may have been a period of rapid construction in which galaxies assembled, lit up, and changed their surroundings with startling speed. That possibility is what keeps this subject alive, because once bright early galaxies are no longer treated as isolated curiosities, the next layer is unavoidable. If some of these systems were not just present, but already built up enough to look mature, then the problem is no longer only about visibility. It becomes a problem about aging, exhaustion, and how a galaxy can seem old while the universe around it is still young. A galaxy only about 1 billion years after the Big Bang should not already feel tired. It should still be assembling, still pulling in gas, still turning that gas into young hot stars at a strong pace. That is the picture many people carry in mind when they think about the early universe. Young universe, young galaxies, fresh systems, active systems, a long future still ahead of them. And yet Webb has been finding hints that some early galaxies do not just look present. They look as if they have already lived through a great deal. That impression has to be handled carefully, because words like old, mature, or dead can create the wrong image if they are not explained. Astronomers are not saying that these galaxies are ancient in the everyday sense. A galaxy seen when the universe was about 1.2 billion years old cannot itself be older than that. What they mean is more specific. Some of these systems appear to have formed a large share of their stars very early, very quickly, and then slowed down or nearly stopped. In modern astronomy, that kind of galaxy is often called quiescent. It is not producing stars at the vigorous rate expected for a system still in an age of rapid cosmic growth. That is what makes the discovery so difficult to ignore. The problem is not simply fast birth. It is fast birth followed by rapid change. Webb did not invent the idea of quiescent galaxies. Nearby astronomy has known them for a long time. In the local universe, many large elliptical galaxies are dominated by older stellar populations and show little ongoing star formation. The surprise is where Webb is seeing possible analogues. Instead of finding them only after the universe has had several billion years to build, merge, enrich, and settle, astronomers are now studying candidates from much earlier epochs. One widely discussed result came in 2024, when researchers using Webb reported a spectroscopically confirmed quiescent galaxy at redshift about 7.3, corresponding to roughly 700 million years after the Big Bang. That claim mattered because spectroscopy gives much firmer footing than photometric hints alone. That is the kind of measurement that changes the tone of the conversation. A bright galaxy can still leave room for debate about stellar mass, dust, emission lines, or model assumptions. A candidate quiescent galaxy raises a tougher chain of implications. To reach a low star formation state that early, the system first had to gather gas efficiently, then convert a great deal of it into stars quickly, then either lose access to fresh cold gas or heat that gas enough to suppress further star formation. In other words, the galaxy did not merely appear early. It appears to have already passed through one of the central life cycle transitions that galaxies normally take longer to reach. That transition is known as quenching. In the nearby universe, astronomers have several candidate mechanisms for it. Gas can be used up rapidly in a burst of star formation. Supernova explosions and stellar winds can stir or expel gas. A central black hole can inject energy into its surroundings and heat gas so that it no longer cools and collapses easily into new stars. Mergers can alter structure, trigger bursts, and then help shut things down. Dense environments can strip gas away. None of these ideas are new. What Webb is doing is forcing them into a far tighter time budget. That time budget is the real strain in the story. To produce a quiescent galaxy by about 1 billion years after the Big Bang, nature has to move through several demanding steps with very little delay. Dark matter halos must collapse early enough. Gas must flow inward efficiently enough. Star formation must proceed at a high enough rate to build up substantial stellar mass. Metals and dust may accumulate. A central black hole may grow. Then, the same galaxy must reach a point where star formation fades or stops. When astronomers look at such an object, they are not just seeing a galaxy that exists. They are seeing a schedule that seems compressed. That is why the word mature keeps returning, even though it needs to be translated carefully every time. Mature does not mean peaceful or fully settled. It means the observed light suggests a stellar population and star formation history, more evolved than expected for that epoch. In some cases, this comes from the overall shape of the spectrum. Galaxies full of very young stars tend to glow strongly in ultraviolet light. Galaxies dominated by older stellar populations show different spectral features, including stronger breaks in the continuum and a different balance of colors. Webb's infrared instruments are especially powerful here because the signatures of very distant stellar populations are shifted into the range Webb can observe. That allows astronomers to move past simple detection and begin asking what kinds of stars are actually producing the light. Even so, this is exactly where scientific discipline matters most. The observation and the interpretation are not identical. The observation might be that a galaxy has a spectrum consistent with weak current star formation and a substantial earlier stellar population. The interpretation is that the system is genuinely quiescent or nearly so, and that much of its growth happened rapidly before the observed moment. The stronger speculation would be that standard galaxy evolution models are missing a major piece of physics, or that cosmology itself requires revision. Those are not the same level of claim, and they should not be spoken as if they are. Still, even the careful version is powerful enough. If Webb is really finding multiple early galaxies whose main stellar populations formed fast and then faded into quiescence, that means the early universe may have been capable of producing not just vigorous star formation, but also rapid exhaustion or suppression of it. It means the first billion years may already contain a surprisingly broad range of galactic states. Some systems still blazing with newborn stars, some building mass at extreme speed, and some already entering a quieter phase after an intense opening run. That possibility reshapes the emotional geometry of the early universe. Before Webb, the opening era of galaxy formation was often imagined in a fairly simple way. Small galaxies ignite first. Larger systems emerge gradually. Star formation remains generally strong in the youthful universe. Quiescent giants belong later, after more time has passed for feedback, mergers, and structural change. Webb has not erased that framework, but it has complicated it. The first billion years now look less like a single stage and more like a crowded developmental period with multiple pathways unfolding at once. There is also an observational reason this matters beyond the charm of the paradox. Quiescent galaxies are not just curiosities. They are records of earlier activity. A system that has already slowed its star formation by redshift 7 must have experienced an even more intense earlier phase that Webb may or may not have caught directly. So these galaxies function almost like compressed archives. They tell astronomers that the unseen phases before them may have been even more extreme than the already startling snapshots Webb is collecting. In that sense, a quiet galaxy in the early universe is not a calm object. It is the aftermath of something fast. The mechanism behind that speed is still being worked out. Some simulations are now being updated to allow earlier and more efficient star formation in dense halos. Others examine whether active galactic nuclei, driven by growing black holes, could quench early systems more strongly than expected. There is also the possibility that some galaxies are not fully dead, but temporarily dimmed, obscured, or observed during a brief phase that mimics stronger quiescence than is really present. This is why astronomers keep demanding spectroscopy, larger samples, and careful modeling instead of relying only on dramatic first impressions. Good cosmology advances by narrowing uncertainty, not by protecting it. The historical context makes this moment even more striking. For decades, the first billion years of the universe were a region mostly described through partial glimpses and models. Hubble pushed deep into that territory, but it could not do Webb's job at Webb's wavelength, range, and sensitivity. Webb was built to examine cosmic dawn more directly, and one of the first things it has done is reveal that our prior mental picture may have been too orderly, not necessarily wrong in its foundations, but too smooth in its pacing. Real galaxies may have moved through their earliest stages with bursts, interruptions, and transformations strong enough to make neat textbook timelines look overly polite. So how could a galaxy already be old when the universe was still young? Because in astronomy, old is often a statement about history rather than sheer age. It means the galaxy's light suggests that the main work of star formation happened earlier than expected, rapidly enough that by the time we see it, the system is no longer behaving like a freshly ignited galaxy. Webb is teaching us that cosmic youth did not guarantee galactic youth. Some galaxies may have lived through their most productive period almost immediately, then changed course while the universe around them was still in its opening billion years. That is what makes these objects so unsettling in the most productive scientific sense. They imply not just early existence, but early sequence. Collapse, inflow, starburst, enrichment, structural change, and declining star formation may all have happened on compressed timelines. And once that becomes plausible, the pressure moves outward. It is no longer only about whether galaxies formed quickly enough. It becomes harder to ignore another possibility. Perhaps some of them were not just aging fast. Perhaps they were turning gas into stars with an efficiency that our standard pictures have still not fully captured. A bright early galaxy is one kind of problem. A galaxy that seems to have built a large stellar mass very early is a more demanding one. Because then the issue is no longer only what Webb saw. It becomes a question of supply, timing, and physical efficiency. How much ordinary matter was available inside the halo that hosted the galaxy? How fast could that gas cool? How much of it could avoid being blown back out by young stars, supernovae, or a growing black hole? And how much of that limited material could actually end up locked into stars before the universe was even 1 billion years old? That is the layer where the story becomes difficult in a deeper way. The telescope can show us light. From that light, astronomers infer stellar populations, star formation histories, and approximate stellar masses. But once some early Webb galaxies began to look not just bright, but substantially built up, the pressure moved from headline surprise to physical accounting. If the inferred masses are even roughly right, then the early universe may have been converting gas into stars with an efficiency that pushes hard against the most comfortable versions of standard galaxy formation models. Some papers have framed this as a genuine tension between observed stellar masses and the baryon supply expected inside early dark matter halos. To understand why that matters, it helps to start with a simple limit. In the standard cosmological picture, dark matter provides most of the gravitational scaffolding for galaxies. Ordinary matter, the baryons that make gas, stars, planets, and people, falls into those dark matter halos. But baryons are only a minority component of the cosmic matter budget. Measurements from modern cosmology imply that only about 1/6 of the matter associated with a halo is ordinary matter, with the rest in dark matter. So even before cooling, collapse, feedback, or star formation begin, nature has already placed a ceiling on the raw material available for building stars. That ceiling is not a technical footnote. It is the first gate in the whole process. A halo can only host a certain amount of baryonic mass to begin with. Then the real losses start. Some gas stays hot. Some does not cool efficiently enough. Some is prevented from collapsing by radiation backgrounds. Some is stirred by turbulence. Some is ejected by stellar feedback. In ordinary conditions, only a fraction of the available baryons become stars. That is why a very massive stellar population in a very early galaxy immediately raises a severe question. Did that system manage to convert an unusually large share of its baryons into stars? And if so, how? This is where the phrase star formation efficiency becomes central, but it needs to be handled carefully. It does not mean that every atom of gas is instantly transformed into stars. It refers to how effectively a galaxy, within its halo and over its history, turns available gas into long-lived stellar mass. Early Webb-based discussions became especially intense when some candidate galaxies at redshifts around 7 to 9 were inferred to have stellar masses so high that the implied efficiency approached extreme values. In some interpretations close to unity for the baryons expected in their host halos. That is why these objects drew so much attention. Not because one number looked dramatic, but because the implied bookkeeping started to feel uncomfortably tight. And yet this is exactly where careful scientific restraint matters. The observation is that Webb has found luminous, very distant galaxies, including systems with substantial inferred stellar masses. That much is real. The interpretation is that some of them may require exceptionally efficient early assembly. The stronger claim, that physics as we know it should not allow such galaxies to exist, goes further than the data currently force us to go. A recent analysis argued that there is still no compelling evidence that star formation efficiency at very high redshift must exceed what careful modeling can accommodate, even if Webb has clearly shifted the discussion by showing more early luminous systems than many expected. So the real problem is not a slogan like, "Physics should not allow this." The real problem is narrower and, in some ways, more interesting. Given the halo growth rates expected in lambda cold dark matter, the available baryon fraction, and the usual losses from feedback, can early galaxies build up their observed stellar masses quickly enough? That is a mechanism problem. It is about rates, not metaphors. The chain begins with halo assembly. In the standard picture, Small density fluctuations in the early universe grow through gravity. Dark matter collapses first, creating halos that then attract ordinary gas. The deeper the halo, the more effectively it can pull matter inward, but the earliest times impose a brutal schedule. There are fewer massive halos available, and less time for mergers and gas inflow to accumulate large reservoirs. If a galaxy looks heavily built up at redshift 10, or even at redshift 7 or 8, then either it formed in one of the rare, earliest halos, or the conversion from halo gas to starlight happened with unusual speed, or both. Then comes cooling. Gas cannot form stars efficiently while it remains too hot and diffuse. It has to radiate away energy, condense, fragment, and reach dense molecular phases. In the early universe, this process depends on metallicity, radiation fields, gas density, and the thermal history of the halo. Primitive gas can cool, but not always as easily as chemically enriched gas in later galaxies. That means the first major stellar populations are not guaranteed to form with the same rhythm as galaxies much later in cosmic history. So when Webb suggests that some systems assembled rapidly anyway, astronomers are not just surprised by the result. They are forced to revisit the details of the cooling path itself. Then comes the most difficult step of all: survival against feedback. The first generations of stars do not quietly help their host galaxy grow. They push back. Massive young stars emit intense radiation. Supernovae inject energy and momentum into the surrounding gas. Those processes can regulate or suppress further star formation, especially in smaller systems. In many models, feedback is one of the main reasons galaxies do not convert all their gas into stars. So, if some early galaxies really did achieve high stellar masses quickly, then feedback may have been less effective in certain halos, or inflow may have replenished gas fast enough to overcome it, or the halos themselves may have been more favorable environments than many simplified forecasts assumed. That is why the baryon budget matters so much. It is not a decorative theoretical phrase. It is the attempt to count what the galaxy could, in principle, have had to work with. When early stellar mass estimates rise high enough, the argument stops being about taste and becomes about arithmetic. A halo of a given mass contains only so many baryons on average. If the inferred stellar mass consumes an implausibly large fraction of that supply, especially after accounting for realistic inefficiencies, then something in the chain has to give. Perhaps the halo mass was underestimated. Perhaps the stellar mass was overestimated. Perhaps the conversion efficiency was genuinely extreme. Or perhaps the abundance of suitable halos at early times was larger than older assumptions suggested. And this is exactly where the field has become more disciplined since the first wave of Webb excitement. Early claims often leaned on photometric mass estimates, which are valuable but model-dependent. Emission line contamination, dust assumptions, stellar population choices, and star formation histories can all shift the inferred mass. Later work has not erased the tension, but it has made the conversation more exact. Some of the earliest, apparently impossible galaxies became less impossible under improved modeling. Others remain difficult enough to keep the pressure on theory. That is a healthier scientific position than either extreme. Not everything is broken, and not nothing interesting happened. Webb has exposed a region where the numbers still need to be reconciled carefully. There is another reason this matters beyond one class of galaxies. The same mechanism question runs through the whole early universe. If star formation was more efficient in dense early halos, that would affect the buildup of stellar mass density, the production of ionizing photons during reionization, the enrichment of gas with heavier elements, and the growth environments of early black holes. One change at the level of gas-to-star conversion does not stay local. It propagates across the opening history of galaxies. That is why this part of the story feels more fundamental than a single striking image. It asks whether the young universe was simply brighter than expected, or whether it was physically better at making stars. The possible answers are no longer just theoretical curiosities. Some recent work has explored whether modified assumptions about early structure growth, small-scale power, or other cosmological ingredients could ease the tension by producing more massive halos earlier. Other studies push in the opposite direction and argue that the existing framework may still be sufficient if stellar masses and efficiencies are interpreted more conservatively. That is the present state of the field. The pressure is real. The final diagnosis is not settled. So did the first galaxies build stars faster than physics should allow? The strongest answer is that Webb has forced astronomers to test that possibility seriously, because some early galaxies appear to demand a pace of assembly that makes the baryon budget and the feedback problem impossible to ignore. But the phrase "should allow" needs discipline. The laws of physics have not failed. What is under strain is a particular set of expectations about how efficiently early halos turn limited ordinary matter into stars. That may end up requiring better mass estimates, better galaxy formation modeling, or a broader rethink of early structure growth. And once the pressure reaches that level, another ingredient begins to stand out more sharply. If some galaxies assembled stars this quickly, it becomes much harder to keep black holes out of the story, because they may not have been late passengers in these systems at all. A young galaxy is already a challenge. A young galaxy with a feeding black hole at its center is a more difficult one. Because now the universe is not only building stars, gas clouds, and structure at high speed, it also seems to be building compact gravitational engines that can pull matter inward, heat it to extreme temperatures, and send out radiation strong enough for Webb to detect across almost the entire history of the cosmos. That is why this part of the story matters so much. It is not only about finding black holes early. Astronomers have expected black holes to exist in the early universe for a long time. Massive stars die. Dense remnants form. Some of those remnants should grow. The real tension is about timescale and scale together. How quickly could a black hole seed appear? How fast could it gain mass? And how could it become visible inside a galaxy that is itself still in the opening stages of assembly? One of the clearest cases is GN Z11. This galaxy was already famous before Webb as one of the most distant known systems from the Hubble era. Webb then observed it with much greater power. In 2024, an extensive JWST near-spec analysis reported spectral features in GN Z11 at redshift about 10.6 that are consistent with an accreting black hole. The same work argued for a black hole of a few million solar masses in a galaxy seen only about 440 million years after the Big Bang. That is not a vague suggestion pulled from color alone. It comes from spectroscopy, including high ionization features and evidence for very dense gas associated with an active galactic nucleus. That observation matters because accretion is not a decorative extra. A black hole becomes visible in this context only if gas is falling inward and releasing energy. Matter spirals into the central region, heats through friction and compression, and radiates strongly, often across a wide range of wavelengths. So when Webb sees signs of an active nucleus in a galaxy this early, it is seeing a compact object that is not merely present. It is already participating in the gas economy of its host. The black hole is feeding while the galaxy is still young. That compresses the timeline in a new way. A galaxy that forms early is one challenge. A galaxy that forms early and already hosts an accreting central black hole implies that several processes are running in parallel. Gas must collapse into the halo. Stars must form. Some compact remnant or seed black hole must exist. Gas must be funneled inward to the center. The environment near the black hole must become dense and energetic enough to produce the spectral signatures Webb can recognize. All of that has to happen while the universe is still within its first few 100 million years. The observation is that GN Z11 shows strong evidence for an accreting black hole. The interpretation is that black hole growth may have started very early and may have been efficient enough to produce a few million solar mass object by redshift 10.6. The stronger speculation is that such cases point directly to unusual seeding channels, such as heavy black hole seeds or extended periods of super Eddington growth. Those are serious possibilities, and the Nature paper explicitly discusses both light seed and heavy seed scenarios, but they are still model-dependent explanations rather than direct measurements of origin. A stellar remnant seed, born from the death of a massive star, starts small. To reach millions or billions of solar masses quickly, it has to grow at an extraordinary pace. In principle, black holes can grow by accretion and mergers. In practice, there are limits. Radiation from infalling gas can push back on additional inflow. Fuel has to be delivered to the center. Feedback can interrupt the process. That is why early active black holes have been such a persistent problem in cosmology even before Webb. Webb has not invented the problem. It has moved it closer to the opening pages of cosmic history. The story becomes even richer once GN Z11 is placed beside another Webb-era population, the so-called little red dots. These are compact, red, high redshift sources found in JWST surveys, especially around redshifts roughly 3 to 9, and they have become one of the most discussed new populations in extragalactic astronomy. Many appear too compact, too red, and in some cases too spectrally unusual to fit comfortably into a simple picture of ordinary star-forming galaxies. A growing body of work has suggested that many of them are faint, active galactic nuclei or black hole-dominated systems, rather than just dusty galaxies. At the same time, their exact nature is still being worked out, and not every little red dot can be treated as a solved case. That uncertainty is important. The phrase, "little red dots," can tempt people into talking as though Webb has already found a settled new class of early supermassive black holes and closed the case. The real situation is more careful than that. Some recent work strongly supports the idea that at least part of this population consists of young supermassive black holes embedded in dense ionized cocoons of gas. Other studies emphasize that the nature of little red dots remains open and that different mechanisms may contribute across the population. So the safe conclusion is not that every compact red source is a black hole. The safe conclusion is that Webb has uncovered a substantial and scientifically disruptive population in which black hole activity appears to play a major role more often than many astronomers expected. Another reason this branch of the story keeps deepening is that some early black holes seem overmassive relative to their host galaxies when compared with the relation seen in many nearby systems. In late 2024, Nature reported a dormant, overmassive black hole in the early universe, highlighting that several recently observed early supermassive black holes may sit above the familiar local black hole to stellar mass relation. That matters because it suggests the central black hole and the host galaxy may not always grow in step, at least not in the early universe. The black hole may surge ahead. If that pattern holds up, the implication is large. In the nearby universe, astronomers often speak of black holes and galaxies as though they co-evolve through a long mutual history. But Webb's early universe may be showing a less orderly opening act. Instead of black holes quietly following galaxy growth, some may have been among the fastest growing structures in the system. They may have influenced gas supply, central density, and feedback earlier than many models assumed. That does not mean the local relations are wrong. It means the road toward those relations may have been more uneven than nearby galaxies alone would suggest. This is also why the black hole story feeds directly back into the galaxy story. A central active nucleus is not just a passenger. Accretion can heat surrounding gas, drive outflows, alter star formation, and complicate the interpretation of the host galaxy's light. Once black holes enter the frame, some of the earlier tension about mature galaxies and rapid stellar assembly may no longer be explainable by starlight alone. Part of what looks like galaxy evolution may also involve compact nuclear activity changing the spectrum, the energy budget, or the apparent state of the host. So why are black holes showing up so soon after the Big Bang? The strongest answer is that Webb is now sensitive enough to catch the signatures of accretion in the early universe, and those signatures reveal that black hole growth was already underway inside some very young galaxies. GN Z11 shows that clearly. The little red dots suggest that such behavior may not be rare, and the reports of overmassive or unusually prominent early black holes raise the possibility that central black holes sometimes grew faster or earlier than the galaxies around them would lead us to expect. The harder question is not whether early black holes existed, it is how they got there so quickly. Perhaps some began from unusually heavy seeds. Perhaps some passed through episodes of accretion above the usual Eddington limit. Perhaps dense early environments delivered fuel more efficiently than many models assumed. Perhaps several of these pathways operated at once. Webb has not solved that problem yet. What it has done is remove the comfort of delay. Black holes were not waiting in the wings for galaxies to finish growing. In at least some cases, they were already active while the first large systems were still trying to take shape. And once that becomes part of the picture, another layer becomes harder to avoid. If galaxies and black holes were both evolving at this pace, then the structure of those early systems may have been stranger than the old tidy images of cosmic dawn ever allowed. The early universe was supposed to be busy. It was supposed to be full of collisions, inflowing gas, intense star formation, and rapidly changing structure. That does not mean astronomers expected it to be featureless. It means they expected many young galaxies to look irregular, clumpy, and still in the act of assembling themselves. So when Webb began returning images in which some early galaxies appeared flattened, centrally concentrated, or even divided into something like an inner core and an outer disk, the tension changed shape. It was no longer only about how much mass these systems had built. It was about whether some of them were already organizing themselves on schedules that looked uncomfortably fast. This needs careful wording from the start. Webb has not shown that the first galaxies all looked like tidy present-day spirals. It has not shown that the early universe was neat. In fact, large studies using JWST still find a substantial population of irregular and peculiar galaxies at high redshift. But Webb has also made something much harder to ignore. Alongside the clumps and asymmetries, there is more evidence for structured morphology earlier in cosmic history than many viewers had been conditioned to expect from older images and older simplified narratives. That shift became especially interesting because Webb is not just seeing these galaxies at greater depth. It is seeing them in the infrared with enough sharpness to examine their rest frame optical light at high redshift. That matters because rest frame optical emission traces the underlying stellar body of a galaxy more reliably than ultraviolet light alone, which can overemphasize bright star-forming knots. In other words, Webb is helping astronomers distinguish between a galaxy that only looks chaotic because the youngest stars dominate the image and a galaxy whose deeper stellar structure is already beginning to settle into something more organized. One broad result came from early JWST morphology studies, which found that disk-like classifications remained surprisingly common across large redshift ranges, even while irregular systems stayed important. A 2024 Astrophysical Journal study reported that disk galaxies accounted for a large fraction of the population in JWST fields, while also noting that the mix changes with mass and redshift. Another 2024 analysis using JWST-based morphologies at matched rest frame wavelengths confirmed that peculiar galaxies become more common toward higher redshift, but did not find a universe devoid of disks or bulges. Those two results fit together better than they seem to at first glance. The early universe can be both more irregular than the nearby universe and still more structurally developed than older visual expectations suggested. That distinction matters because order in astronomy is rarely absolute. A high redshift disk does not have to be a thin, fully settled, grand design spiral to count as evidence of organization. A galaxy can be rotationally flattened, centrally concentrated, or built in an inside-out pattern without yet resembling a calm local spiral. Webb's contribution is that it lets astronomers ask which parts of that structural sequence were already underway early on. A particularly striking example came in 2025, when Nature Astronomy published evidence for a star-forming galaxy in the epoch of reionization, showing a core embedded in a disk. The study argued that the galaxy displayed rising specific star formation toward its outskirts, consistent with inside-out growth, where a central protobulge or dense core forms, while the surrounding disk continues active star formation. That is a very specific kind of maturity. Not the maturity of a fully finished galaxy, but the maturity of internal differentiation. Different regions of the system appear to be doing different jobs already. The observation is that Webb images and profile fitting reveal some early galaxies with structural components that can be modeled as disks, central concentrations, or mixed morphologies. In at least some cases, follow-up analysis suggests inside-out growth rather than a single undifferentiated blob of stars. The interpretation is that certain galaxies may be establishing ordered stellar structure earlier than many pre-Webb mental pictures allowed. That is an important claim, but still a measured one. It does not mean the early universe was broadly settled. It means some systems may have reached recognizable structural stages quickly. The stronger speculation would be that current galaxy formation models fundamentally underestimated how fast-ordered morphologies can emerge, or that entirely new physics is needed to explain them. That remains open. Some of the tension may come from older expectations being too visually simplistic rather than from the core cosmological framework failing. To understand why order appears at all, it helps to think about what a disk is physically. A disk forms when gas falling into a dark matter halo carries angular momentum. As the gas cools and contracts, that angular momentum prevents it from collapsing straight to the center. Instead, the material spreads into a rotating flattened structure. In a simple picture, this sounds natural. In a realistic early universe picture, it is harder. Gas arrives in streams, mergers disturb the system, star formation injects energy. Feedback from young stars and black holes can stir or expel gas. So, when a disk-like structure appears early, the interesting part is not that disks are impossible. It is that some galaxies seem to have retained or rebuilt ordered rotation, despite living in an era of frequent disruption. That may be why recent work on disk evolution with JWST has become so valuable. A 2025 study highlighted structural evidence that thick disks may appear first, with thinner disk components emerging later, and that more massive systems can progress along this path earlier than less massive ones. Another 2025 Nature Astronomy paper reported a giant disk galaxy only about 2 billion years after the Big Bang, with spiral morphology and rotational velocity consistent with a local Tully-Fisher-like relation. That object is later than the epoch of reionization, so it does not belong to the very first galaxies. But it strengthens the broader lesson that ordered rotating systems can emerge early and sometimes on unexpectedly developed terms. There is a caution here. Shape alone can mislead. A compact galaxy can look regular in projection without being dynamically settled. A bright central region can suggest a bulge even when it is really a dense star-forming core. A flattened light profile can hint at a disk without proving that the system is rotationally supported. That is why astronomers increasingly try to connect morphology with kinematics, spectroscopy, and resolved star formation structure rather than relying on images alone. Order in appearance is more convincing when it is matched by order in motion. This is one reason Webb's morphology results feel so disruptive without yet being reckless. They do not merely say that some galaxies look pretty. They suggest that the timescale for internal differentiation, disk building, and perhaps bulge or core formation may be shorter than many people imagined. The universe in its early phase may still have been messy in the large statistical sense, but it was apparently capable of producing pockets of organization while that mess was still ongoing. That is a subtler and more powerful statement than saying the early universe looked settled. There is also a deeper implication beneath the images. Structure is memory. A disk remembers angular momentum. A core remembers intense early central buildup. An inside-out profile remembers where gas was turned into stars first and where star formation continued later. So when Webb sees early galaxies with these traits, it is not only showing what they look like, it is revealing traces of the physical histories that built them. A system with a central core and a star-forming outer disk is not just visually interesting. It implies that inflow, collapse, feedback, and star formation had already become spatially organized within that galaxy. That is why this branch of the Webb story is relevant to earlier debates about stellar mass, still states, and black holes. If some galaxies were building stars at high efficiency, and if some were already shutting down central star formation or growing active nuclei, then internal structure should start to matter more, not less. Morphology becomes the visible imprint of those earlier processes. The shape of the galaxy begins to record the history of how gas moved, where stars formed, and which parts of the system changed first. So why do some early galaxies already have disks, cores, or ordered structure? Because the early universe, although highly dynamic, was still governed by the same basic ingredients that shape galaxies later on: gravity, gas inflow, angular momentum, cooling, feedback, and time. Webb is showing that in some systems, those ingredients combined quickly enough to produce recognizable organization much earlier than many simplified pictures suggested. Not universal calm, not modern perfection, but real internal structure emerging while cosmic assembly was still intense. And that leaves the listener with a sharper version of the discomfort. The old contrast between young universe and mature galaxy is becoming harder to preserve. Some galaxies were not only present early, not only bright early, not only forming stars and black holes early, they were also beginning to look structurally differentiated early. Once that is allowed into the story, another layer starts to press forward. A universe that can produce ordered galaxies this soon may also have been changing its larger environment sooner than expected, because galaxies with this kind of internal activity are not passive lights in the dark. They are engines that affect the gas around them and eventually the state of the universe itself. The early universe was not dark in a simple sense. It had light. The first stars formed, the first galaxies began to shine, and radiation was already moving through space. But for a long time, that light was trapped inside a fog of neutral hydrogen that filled the space between galaxies. If you could have seen that era directly, the problem would not have been a lack of sources. It would have been the condition of the medium itself. The young universe was full of hydrogen atoms whose electrons were still bound to their nuclei, and that neutral gas was very effective at absorbing ultraviolet radiation. That is why reionization matters. It names one of the largest transitions in cosmic history. As the first generations of luminous sources formed, their energetic photons began stripping electrons from neutral hydrogen in the intergalactic medium. Little by little, bubble by bubble, the fog thinned. Regions around galaxies became ionized. Over time, those ionized regions grew, overlapped, and connected until most intergalactic hydrogen was no longer neutral. This was not a decorative side event. It was the moment when the universe became transparent to ultraviolet light over vast distances. Before Webb, astronomers already had a rough outline of that transition. Observations of the cosmic microwave background from Planck constrained the overall timing, while distant quasars and earlier galaxy surveys suggested that reionization was largely underway within the first billion years. But the exact pace, the main sources, and the degree of patchiness remained uncertain. Were ordinary early galaxies enough? Did very faint galaxies do most of the work? How much did bright galaxies contribute? Those questions were open because the sources responsible were hard to count and even harder to characterize. Webb changed that immediately by pushing deeper into cosmic dawn. One of the most important results was the spectroscopic confirmation of JADE SGSZ140 at redshift about 14.3, seen when the universe was less than 300 million years old. This was not just another distant object added to a record list. It showed that surprisingly ultraviolet bright galaxies already existed extremely early. That matters because ultraviolet output is exactly the kind of radiation needed to ionize hydrogen, at least if enough of it escapes from the galaxy into surrounding space. A very early luminous source does not prove that reionization finished early, but it does apply pressure to older assumptions about the opening pace of the process. If galaxies this bright were already in place beyond redshift 14, then the young universe may have started producing significant ionizing radiation sooner, and perhaps in more intense pockets, than many models had assumed. A 2025 Nature paper put this directly. Recent Webb observations have shown that surprisingly, UV-bright galaxies were in place beyond redshift 14, when the universe was under 300 million years old. But brightness alone is not enough. That is where good cosmology has to slow down and resist the easy version of the story. reionization depends on at least four linked quantities. First, how many galaxies existed at a given epoch. Second, how many ionizing photons their stars produced. Third, what fraction of those photons escaped from the dense gas of the galaxy into intergalactic space. And fourth, how rapidly the ionized hydrogen recombined and became neutral again in the clumpy cosmic medium. So a luminous galaxy is important, but it is not a complete answer. One galaxy can announce that strong sources existed early. It cannot by itself tell us whether the universe as a whole had already been largely cleared. This is why recent Webb-era results are so interesting. They do not only show bright galaxies, they also begin to show signs of local ionized bubbles around some of them. In March 2025, NASA highlighted Webb observations of JWST GS-Z131, a galaxy seen about 330 million years after the Big Bang, where the detection of Lyman alpha emission suggested that the galaxy had carved out an unexpectedly large ionized region around itself. That matters because Lyman alpha photons are usually scattered and suppressed if the surrounding intergalactic medium is still strongly neutral. To see that line escape, something about the local environment must already be more transparent than a simple, uniformly neutral picture would suggest. That does not mean the entire universe was already ionized at that time. It means reionization may have been patchy from very early on, with individual galaxies or small groups of galaxies creating transparent bubbles inside a still mostly neutral cosmos. This is a very different image from a clean global switch flipping all at once. The process may have begun in islands of radiation that expanded outward, leaving large neutral regions in between for quite some time. Webb is valuable here because it is not only counting sources. It is beginning to glimpse the interaction between those sources and the intergalactic medium around them. That patchiness matters because it changes how the phrase faster reionization should be understood. The source text is right to ask whether Webb is revealing a universe that reionized faster than expected, but the most careful version is more precise. Webb may be showing that reionization began vigorously in some places earlier than many people imagined, and that the brightest young galaxies could contribute more strongly to the process than older simplified pictures allowed. That is not the same as saying the whole universe reionized uniformly and quickly everywhere. It may instead mean that the opening phase was earlier, more intense, and more uneven. JWST GS-Z140 sharpens that pressure even more. Follow-up mid-infrared observations with MIRI showed strong rest-frame optical light from this galaxy, offering more information about its stellar population and physical state. The point here is not that one object explains reionization by itself. The point is that the existence of such a luminous system at that epoch makes it harder to keep the first few 100 million years emotionally empty. By that time, the universe was already capable of building galaxies bright enough to matter for large-scale radiation budgets. There is another point here. The strongest candidates for driving reionization may not have been only the brightest galaxies. Many models still suggest that numerous fainter galaxies could have contributed a large fraction of the ionizing photons. Webb's discoveries do not necessarily overturn that. What they do is widen the plausible role of bright systems and make the early ultraviolet landscape look richer than expected. A universe with unexpectedly luminous galaxies beyond redshift 14 is not automatically a universe explained by rare giants alone. It is a universe in which the upper end of the luminosity distribution appears active earlier than many forecasts suggested. Webb has securely confirmed very distant galaxies, including JWST 140. Webb has shown that some of these galaxies are surprisingly UV bright at extremely early times. Webb has also found cases, such as JAD ESGS-Z131, where the local environment appears more ionized than a naive picture would have predicted. From those observations, astronomers infer that the early universe may have begun large-scale reionization sooner or in a more vigorous and patchy way than many earlier models assumed. The stronger claim, that the entire standard timeline is broken, still goes beyond what the current evidence requires. That distinction between observation and interpretation is important because reionization is a collective process. It is one of the few stories in cosmology where the space between galaxies matters just as much as the galaxies themselves. A source can be brilliant and still fail to change the wider universe efficiently if its ionizing photons remain trapped. A more modest galaxy can matter greatly if enough radiation escapes. The central difficulty is not only to find the first galaxies, but to understand how effectively their light leaked into the hydrogen around them. That is the hidden accounting problem inside the drama. So is Webb revealing a universe that reionized faster than we thought? The strongest answer is that Webb is revealing a universe in which the ingredients for reionization were already in place very early, including unexpectedly ultraviolet bright galaxies and at least some evidence for local ionized bubbles when the universe was still under about 330 million years old. That does not yet prove that the whole cosmos cleared earlier in one simple sweep. It does suggest that the first large-scale lighting of intergalactic space may have begun more energetically and in a more uneven pattern than many older pictures allowed. And that's what gives the Webb family story its real power. Early galaxies are no longer only objects sitting at the edge of visibility. They are becoming agents. Their light does not merely tell us that they existed. It begins to tell us what they were doing to the universe around them. Once that shift happens, the tension widens again. Because if galaxies were already bright enough to reshape intergalactic space this early, then the next issue is no longer only how early they appeared. It becomes whether the larger framework of cosmic timing itself is being nudged from several directions at once. The James Webb Space Telescope changed the mood of the early universe story, but it did not make one of cosmology's hardest disputes disappear. If anything, it helped remove one of the easier escape routes. Because the Hubble tension was never simply a disagreement about one number. It was a disagreement about whether the universe expands today at the rate predicted when we start from the early universe and evolve the standard model forward, or at the higher rate measured using nearby cosmic distance markers. That mismatch was already troubling before Webb. Webb matters because it was asked to test whether some of the local measurements might be wrong in a familiar and ordinary way. NASA's message in late 2024 was that Webb's new lensed supernova work supported the conclusion that the tension is still with us. To see why that matters, it helps to separate the two sides of the problem. On one side are early universe inferences, especially those based on the cosmic microwave background. In the standard lambda cold dark matter model, measurements of the microwave background allow cosmologists to infer the present expansion rate by fitting a full model of the young universe and projecting it forward. On the other side are late universe measurements, built from objects whose distances can be calibrated more directly, such as Cepheid variable stars and Type Ia supernovae. These two routes should agree if the standard model and the measurements are both correct, but for years they have not lined up cleanly. That persistent mismatch is what people mean by the Hubble tension. Webb entered this story for a practical reason, not because it was built as a dedicated Hubble tension machine. One long-running concern was that Hubble Space Telescope measurements of Cepheids in crowded distant galaxies might contain subtle biases from blending, calibration, or unresolved nearby stars. Webb, with its infrared capability and sharper handling of dusty, crowded regions, offered a way to revisit key steps in the local distance ladder. Earlier in 2024, Webb data on Cepheids and Type Ia supernova host galaxies had already reinforced Hubble's previous local measurement, rather than erasing it. NASA then highlighted a second Webb-based line of evidence in October, a lensed supernova result that again supported the view that the discrepancy is not going away through an obvious calibration fix. That lensed supernova result is worth slowing down for because it is easy to overstate. The basic idea is elegant. If a distant exploding star lies behind a massive foreground galaxy or galaxy cluster, gravity can bend the light and create multiple images of the same supernova. Those images do not arrive at exactly the same time because the light travels along different paths through different gravitational potentials. Measuring those time delays gives astronomers a way to estimate cosmic distances and the expansion rate. This method does not depend on the same ladder in quite the same way as Cepheids and nearby supernova calibration. So when a Webb-supported lensed supernova analysis lands on a value consistent with the higher local expansion rate, it matters because it reduces the comfort of saying the entire tension is probably just a local distance ladder mistake. But this is where discipline matters. The observation is that Webb-supported analyses, including the late 2024 lensed supernova work highlighted by NASA, continue to support the claim that the Hubble tension is real rather than obviously caused by one simple measurement error in the local ladder. The interpretation is that the disagreement may reflect either multiple small systematics spread across methods or a genuine shortcoming in the standard cosmological model. The stronger speculation is that the early universe contained additional physics, such as early dark energy, that altered the sound horizon before recombination and therefore changed the inferred expansion rate from the microwave background. That remains an active theoretical direction, not a settled solution. Webb's early galaxy discoveries do not directly cause the Hubble tension, but both threads push on the same larger question: are our most comfortable pictures of the early universe too smooth, too conservative, or missing an ingredient? The early galaxy story says that some galaxies may have assembled stars, structure, and black holes faster than many expected. The Hubble tension story says that the universe's expansion history may not fit together as neatly as the simplest standard model predicts. These are not identical tensions, but they resonate with each other because both reduce the space for easy confidence. That is why early dark energy keeps returning in these conversations. The idea, in its simplest form, is that the young universe may have contained a temporary extra component of energy density before recombination. If that happened, it would change the expansion rate at early times and reduce the sound horizon imprinted in the cosmic microwave background. Then the same observed angular scale in the microwave background could be reconciled with a higher present-day Hubble constant. This is not science fiction. It is one of the best-known classes of model built specifically to address the tension. But it is also not a solved answer. Recent theoretical work continues to explore how much early dark energy would be needed, how natural such models are, and whether they remain compatible with the full set of cosmological data. Attention in cosmology is rarely one dramatic break. More often, it is a long, narrowing process. One proposed systematic gets tested and looks less convincing. One new dataset arrives and refuses to make the disagreement vanish. One family of theoretical models solves part of the problem but creates strain somewhere else. That is the present state of the Hubble tension. Webb has not solved it. Webb has helped make it harder to dismiss as a minor artifact. That is a subtler result than a revolution, but in real science it can be the more important one. There is also a deeper reason audiences keep following this branch of the story. The Hubble constant is not just another measurement. It sets the present expansion rate of the universe and feeds into how we reconstruct cosmic history. If the value inferred from the early universe disagrees with the value measured more locally, then something in the bridge between those eras may be incomplete. Perhaps a calibration step still needs improvement. Perhaps the discrepancy is distributed across several methods in a way that is hard to untangle. Or perhaps the early universe behaved slightly differently from the simplest lambda cold dark matter picture. Each possibility carries a different weight, but all of them matter because the Hubble constant sits at the center of modern cosmology rather than at its edge. That is why it would be a mistake to force Webb into a role it does not have. Webb did not create the Hubble tension. Webb did not prove early dark energy. Webb did not by itself rewrite the full expansion history of the universe. What Webb did do was test important pieces of the observational case with new tools. In the context NASA emphasized, Webb-supported lensed supernova work and other distance ladder checks did not make the discrepancy fade. They strengthened the sense that the problem deserves to be taken seriously. So, if Webb changed the early universe, why is the Hubble tension still here? Because Webb's job was not to magically reconcile every cosmological disagreement. Its role has been more demanding than that. It has looked again at key observational steps and found that at least some of the old tension survives the new scrutiny. That means the mismatch between early universe and late universe expansion measurements has not been cleanly explained away. And once that remains true, the pressure moves outward again. The story is no longer only that Webb found a more active early universe. It is that cosmology now has fewer easy places to hide from its own unresolved arithmetic. A strange early galaxy can be treated as an isolated surprise. A population of early galaxies that seems too bright or too massive forces a different kind of thought. Because galaxies do not assemble in empty freedom. In modern cosmology, they grow inside dark matter halos, invisible gravitational wells that gather gas, hold it, and help set the stage for star formation. So when Webb finds galaxies that appear to have built up quickly, the pressure does not stay at the level of starlight. It drops into the framework underneath. If the visible structures seem to have arrived too fast, then either we are reading the visible light too aggressively, or the unseen scaffolding and the gas physics inside it are behaving in ways that older, simple expectations did not capture. That is why dark matter enters this story at all. In the standard lambda CDM picture, small density fluctuations in the early universe grow through gravity. Dark matter collapses first, forming halos. Ordinary matter then falls into those halos, cools, and forms galaxies. This means early galaxies are indirect tracers of the halo population. If Webb reveals more bright or massive galaxies at high redshift than expected, one immediate line of inquiry is whether there were more suitable halos or earlier growing halos than standard assumptions seem to allow. Another is whether the galaxies inside ordinary halos were simply more efficient at turning their gas into stars. The key limit here is the baryon budget. A dark matter halo is not made mostly of the stuff that forms stars. Only a minority of its matter is baryonic. In the standard cosmological accounting, the baryonic mass fraction of a massive halo is approximately the cosmic mean, omega b over omega m, which is about 1/6. That number is not a detail. It is the first hard ceiling in the problem. A halo of a given mass only has so much ordinary matter available in principle, and in practice only some fraction of that gas cools, condenses, survives feedback, and ends up locked into stars. That is why some early JWST galaxies drew so much attention. Their inferred stellar masses seemed, in some interpretations, to consume an uncomfortably large share of the baryons their host halos could plausibly contain. This is the point where people often jump too quickly to dark matter must be wrong. That is not the strongest reading of the evidence. The observation is that JWST has found very early galaxies whose luminosities, and in some cases inferred stellar masses, are surprisingly high. The interpretation is that these systems may require either unusually efficient star formation, unusually favorable halo growth histories, or revised estimates of stellar mass and halo connection. The stronger speculation is that the underlying structure growth framework itself may need modification. That remains open. Several papers since the first JWST releases have emphasized that part of the apparent tension can shift depending on how stellar masses are inferred, how bursty the star formation histories are assumed to be, and how one maps observed galaxies onto host halos. Still, the pressure is real, because the dark matter framework is not just a background idea. It predicts a halo mass function, the abundance of halos of different masses at different cosmic times. If galaxies with large stellar masses are common at redshifts around 7 to 10, that feeds directly into the question of whether enough massive halos existed early enough. A 2023 study on early JWST galaxies and cosmology made this link explicit, noting that high redshift galaxy observations can be used to indirectly track the cosmological halo mass function. That is why this section feels deeper than a simple galaxy puzzle. It is not only asking whether one galaxy looks odd, it is asking whether the invisible distribution of gravitational wells in the early universe is being inferred correctly. There are several possible ways the tension could ease without abandoning lambda c d m. The first is that some stellar masses were overestimated, especially in the early wave of Webb analyses when photometry, emission line contamination, and model assumptions could push masses upward. The second is that early star formation may have been more efficient than many pre-Webb galaxy models assumed, allowing a larger stellar yield from ordinary halos without changing the dark matter framework itself. The third is that rare environments, overdensities, or selection effects may make the most dramatic galaxies easier to find than simple average expectations would suggest. Recent comparison work between pre-existing lambda CDM-based galaxy models and JWST ultraviolet luminosity functions shows that some tension remains, but also that model assumptions matter greatly. If early galaxies continue to look too numerous, too bright, or too massive even after better modeling, then astronomers can begin asking whether the small-scale growth of structure was enhanced in the early universe. That does not necessarily mean eliminating dark matter. It could mean revisiting the primordial power spectrum, dark sector assumptions, or the timing of halo formation. More recent work has explored altered matter power spectra, or non-standard early universe ingredients, as ways to generate more suitable high redshift halos. Those studies are best understood as responses to pressure, not as settled replacements for the standard model. That distinction matters because dark matter itself is not one single claim. There is the broad idea that most matter is non-luminous and gravitationally dominant, which remains strongly supported by many lines of evidence outside Webb. Then there is the much more specific question of how rapidly dark matter halos of different masses should appear, and how galaxies should populate them at redshifts above 7 or 10. Webb is acting much more as a test of the second issue than as a clean refutation of the first. In other words, the telescope is not telling astronomers to throw away invisible matter. It is forcing them to tighten the relationship between dark halos, baryonic reservoirs, and visible galaxies at the earliest times. Dark matter is never seen directly in these Webb images. What Webb shows is starlight, gas, dust, structure, and spectra. Yet all of that visible information points back to something unseen, because galaxies are not free-floating lights. Their sizes, growth rates, and abundance are tied to gravitational wells we infer rather than photograph. So when the visible universe starts looking more active than expected, the invisible one immediately comes under review. That is why this is not a detour away from the earlier Webb surprises. It is their hidden continuation. So is dark matter building cosmic structure differently than we expected? The strongest answer is more careful than the headline version. Webb has not shown that dark matter itself is wrong. It has shown that some early galaxies may be difficult to reconcile with the most comfortable assumptions about how fast halos grow, how many baryons they contain, and how efficiently those baryons turn into stars. That leaves several live possibilities on the table. The galaxies may be less extreme than first inferred. Galaxy formation physics may be more efficient or bursty than older models assumed. Or the early growth of structure may need to be adjusted in ways that cosmologists are still actively testing. The telescope did not merely find strange galaxies. It found galaxies that force visible matter and invisible matter back into the same sentence. Once that happens, the discomfort becomes harder to contain. Because if the scaffolding is even slightly different from what we expected, then the story is no longer only about how galaxies formed. It becomes about whether the whole standard picture of cosmic assembly has been drawn a little too neatly from the beginning. For a long time, the simplest version of the universe had one enormous advantage. It was not only elegant, it worked. The standard cosmological model, lambda CDM, said that most of the cosmos is made of dark energy and dark matter, with ordinary matter contributing only a small fraction, and that the accelerated expansion of the universe could be described by a cosmological constant, a steady background term that does not change with time. That picture has been remarkably successful across many observations, which is exactly why the current tension matters. It is not that cosmologists are eager to abandon the model. It is that some new fits are beginning to ask whether the simplest version is still enough. This is where dark energy enters the story in a more careful way than headlines usually allow. Dark energy is the name given to whatever is driving the accelerated expansion of the universe. In the simplest picture, it behaves like a cosmological constant, meaning its energy density remains fixed, even as space expands. In that case, its equation of state parameter, written as W, stays exactly at -1. A different possibility is dynamical dark energy, where W can change with time or redshift. The difference sounds technical, but it changes the long-term behavior of cosmic expansion and alters how the standard model connects early and late observations. DESI matters here because it was built to map the large-scale structure of the universe with extraordinary precision. Its main tool in this context is baryon acoustic oscillations, the faint imprint of sound waves from the early universe preserved in the large-scale distribution of galaxies. Those patterns act like a cosmic ruler. By measuring how that ruler appears at different redshifts, DESI helps reconstruct how the expansion of the universe has changed over time. In March 2025, the DESI collaboration released its DR2 cosmology results based on more than 14 million galaxies and quasars from 3 years of observations, making it one of the most powerful expansion history datasets ever assembled. DESI alone does not simply declare that dark energy is evolving, but when the DESI-BAO measurements are combined with other cosmological probes, such as the Cosmic Microwave Background and Type Ia supernova datasets, some of the best fits begin to prefer a model in which dark energy changes over time rather than remaining perfectly constant. DESI's own March 2025 guide stated that the evidence for dynamic dark energy, especially at low redshift below about 0.3, appeared robust across a range of methods when combined with external datasets. Fermilab's summary of the same result put it more plainly. The combined data suggested that the influence of dark energy may be weakening over time. That is the point where the model begins to feel less rigid, not broken, not overturned, but bent under pressure. Because lambda CDM does not only say the universe expands, it says the late-time acceleration can be explained by a cosmological constant with a very specific behavior. If the data continue to prefer a time-varying dark energy term, then the issue is not cosmetic. It would mean the standard model's simplest interpretation of cosmic acceleration is incomplete. The challenge would not necessarily erase the rest of lambda CDM, but it would force cosmologists to replace one of its most central assumptions with something more flexible. Still, this is exactly where scientific discipline matters. The observation is that DESI-DR2 measured baryon acoustic oscillations with very high precision across a large redshift range, giving a sharper map of expansion history. The interpretation is that when those measurements are combined with other major datasets, some models with evolving dark energy fit better than a perfectly constant cosmological constant. The stronger speculation is that cosmology has already moved beyond lambda CDM and that a new dark energy theory has effectively won. That is not where the evidence stands. Review commentary in 2025 stressed that the hints are intriguing and increasingly difficult to ignore, but not decisive. This distinction matters because cosmology has seen many suggestive signals before. A mild preference in one data combination can weaken when another dataset is added, or strengthen under different model assumptions, or shift depending on calibration choices and parameter priors. DESI's own public communication reflected that balance. On the one hand, the collaboration emphasized that the new analyses were showing a genuine preference for dynamical dark energy in several combinations. On the other hand, the result was presented as a possibility that requires further confirmation, not as a final answer. None of those findings alone proves anything about dark energy. But together, they change the emotional balance of the model. They make the standard picture feel less like a finished map and more like a framework under active stress testing. That is why dark energy belongs here. Not because Webb directly measured it changing, but because the broader cosmological atmosphere has become less comfortable with easy assumptions. There is also a deeper reason the dark energy issue lands so hard. Dark matter shapes structure. Dark energy shapes destiny. If dark energy is a true cosmological constant, then accelerated expansion continues in a very specific way. If it evolves, then the future history of the universe becomes less certain. The acceleration might weaken, strengthen, or follow a more complex path depending on the underlying physics. UK Research and Innovation summarized the 2025 DESI interpretation in exactly those terms. If dark energy evolves with time, the fate of the universe becomes more uncertain than the simple constant will picture suggests. This does not mean cosmologists have identified the new theory already waiting to replace the old one. Many competing ideas exist. Some use parameterized time-varying equations of state, such as the familiar two-parameter W's forms. Some invoke scalar fields. Some try to connect dark energy behavior with deeper modifications of gravity or with broader tensions in the cosmological dataset. The DESI collaboration's own guide noted that a two-parameter time-varying form was sufficient to capture the trends present in the current data. That is useful, but it is a description, not yet a deep physical explanation. A changing dark energy term would affect the foundation of modern cosmology far more deeply than any one surprising galaxy. DESI DR2 has not confirmed that result, but it has pushed the possibility far enough into the data that it can no longer be treated as fringe. So, is dark energy really constant, or are we watching the model bend? The strongest answer is that recent DESI analyses, especially when combined with supernova and microwave background data, are placing noticeable pressure on the simplest constant, LA interpretation. They hint that the influence of dark energy may evolve with time, particularly at lower redshift, but the case is still tentative rather than settled. Lambda c d m is not gone. The cosmological constant has not been disproven. The earlier Webb tensions made the opening universe look more active than expected. DESI now raises the possibility that the late universe may also be less simple than the old textbook form implied. If both ends of cosmic history are beginning to press on the same framework, then the issue is no longer just whether a few galaxies arrived ahead of schedule. It becomes harder to avoid a wider suspicion. Perhaps the universe is not violating the standard model outright, but showing us, piece by piece, where its simplest form may be starting to give. The most careful answer is that Webb has not broken cosmology. It has made cosmology work harder. That difference matters because the telescope did not arrive and erase the standard model of the universe. It arrived and forced that model to face sharper evidence, earlier times, and tougher accounting than before. The result is not collapse. The result is pressure. That pressure is real. Webb has confirmed galaxies from extremely early cosmic time. Some of them appear brighter than many pre-launch expectations allowed comfortably. Some seem to have built stars quickly. Some may already host active black holes. Some show more internal structure than older simplified pictures led many people to expect. Taken together, these findings make the first billion years of cosmic history look more active, more compressed, and more physically demanding than the cleaner version many people carried in mind. But none of that means the universe has escaped the laws of physics. It means our first practical descriptions of early galaxy growth may have been too simple in places. That is a very different conclusion. The standard cosmological model still explains an enormous amount. It describes the expansion of space, the relic pattern in the cosmic microwave background, the large-scale growth of matter, and the broad history of cosmic structure with remarkable success. That is exactly why Webb's results matter so much. If the model were weak, tension would not mean much. The fact that these observations matter tells you how successful the framework has already been. The important issue is where the tension actually lives. In some cases, it lives in interpretation. A galaxy can look extremely bright without automatically having an impossible stellar mass. Emission lines can affect the inferred brightness in particular filters. Dust can change how the light is read. A young stellar population can dominate the spectrum in a way that makes a system look more massive or more evolved until deeper analysis is done. An active black hole can add radiation that complicates the story further. So part of the Webb era has been a lesson in caution. The first dramatic reading of a distant galaxy is not always the final one. That is not a weakness in the science. It is the science. A better telescope does not only give clearer answers, it also reveals where old assumptions were carrying more weight than people realized. Webb has done that repeatedly. It has separated what is directly observed from what must still be inferred. It has made astronomers test stellar masses more carefully, compare photometric estimates with spectroscopy, reconsider how fast gas can cool and form stars, and ask whether early black hole growth and galaxy assembly may have been more efficient than many earlier models assumed. So the strongest conclusion is not that cosmology is broken. It is that cosmology has entered a stricter phase. The early universe now has to be described with fewer shortcuts. That stricter phase is visible across several layers at once. The first layer is galaxies themselves. Webb has shown that very early galaxies were already in place, and some of them were surprisingly luminous. The second layer is star formation. If some stellar masses remain high after careful analysis, then gas must have been converted into stars with notable efficiency inside early dark matter halos. The third layer is black holes. If accreting black holes were already active in very young galaxies, then central growth and galaxy growth were happening together on compressed timescales. The fourth layer is structure. If some early galaxies already had disks, cores, or inside-out organization, then internal differentiation was underway sooner than many simplified visual expectations suggested. The fifth layer is the surrounding universe. If early galaxies were already producing strong ultraviolet radiation, then reionization may have begun vigorously and unevenly in very young cosmic time. Each layer adds pressure, but none of them alone forces a full rejection of the standard model. What they do force is a more careful conversation about where astrophysics ends and where cosmology begins. Some tensions may be resolved by better galaxy modeling. Some may be reduced by revised mass estimates. Some may point to feedback, gas inflow, or black hole fueling being handled too crudely in older simulations. And some may remain sharp enough that broader cosmological assumptions come under stronger review. That is why this story should not be told as a choice between two extremes. It is not everything is fine on one side and everything is broken on the other. Reality is usually harder than that. A scientific framework can remain broadly correct and still need revision in important places. That is normal. Newtonian gravity worked across a huge range of problems and still turned out to be part of a deeper account. Early atomic models explained many facts and still had to be expanded. Science often moves this way. A model becomes powerful. Then a better instrument reaches a domain where the clean version starts to show strain. That is where Webb sits in the history of cosmology. It is not the telescope that destroyed the map. It is the telescope that brought the map closer to the terrain. Sometimes people hear that later papers softened an early claim, and they assume the whole tension was empty. That is too simple. Revision does not mean the original pressure was meaningless. It means the field is doing its job. If one galaxy turns out to be less massive than first estimated, that matters. If one population is more mixed in nature than first headlines suggested, that matters too. But even after these corrections, the overall picture remains more demanding than the old pre-Webb one. The early universe now looks crowded with rapid processes that do not fit easily into the old, comfortable mental timeline. Webb is not the last step. It is the instrument that opened this era. What comes next will decide how deep the revisions have to go. NASA's Nancy Grace Roman Space Telescope will widen the field dramatically. Roman will not replace Webb's depth, but it will survey huge regions of the sky and trace large-scale structure, cosmic expansion, and galaxy populations on scales Webb cannot cover efficiently. That matters because one of the hardest questions in the Webb era is whether the most striking objects are rare exceptions or signs of a broader pattern. Roman will help answer that by giving astronomers statistics, environment, and scale. The extremely large telescope will add another kind of power. With its enormous mirror and advanced instruments, it will study faint, distant galaxies, their gas, their stars, and their kinematics in far greater detail. That matters because some of the current tension depends on what these galaxies really are inside. Are they truly rotationally supported disks? How metal-rich are they? How much gas do they contain? How strong are their outflows? Are there central black holes dominating the light? Those are not decorative details. They are the details that decide whether the present pressure eases or hardens. So the cleanest ending is this. Webb is not showing that cosmology was foolish. It is showing that cosmology was provisional, which is what good science has always been. The Standard Model earned its authority honestly. It survived many tests, explained many phenomena, and gave astronomers a framework strong enough to make real predictions. Webb has now taken that framework into a harsher observational regime. Some parts are holding very well, some parts are being stretched. Some may eventually need repair. That is not a failure of science. It is one of the clearest signs that science is alive. When a scientific model is no longer useful, researchers stop testing it in serious detail. But when a model is still powerful, they examine it more closely each time new evidence appears. That is what is happening here. Webb has brought in observations that are far sharper than before, and cosmologists are responding in the right way. They are rechecking galaxy masses, studying the role of dust, testing different stellar population models, separating black hole light from starlight, improving simulations, and comparing spectroscopic results with earlier photometric estimates. In other words, they are not defending the old picture blindly. They are measuring, testing, and refining it wherever the new data apply the most pressure. And perhaps that is the most important thing this whole journey has been pointing toward. The universe has not become less understandable. It has become less willing to fit inside our first neat summary of itself. That is a harder kind of beauty. Not the beauty of a finished answer, but the beauty of a framework strong enough to survive being questioned. So is Webb breaking cosmology, or showing science working exactly as it should? The best answer is that it is doing both of the important things at once. It is exposing where the cleanest version of the story may be incomplete, and it is showing the scientific method operating exactly as it should under stronger evidence. The tension is real. The caution is real. The revisions are real. And the larger understanding is still growing. As this video comes to its close, I want to thank you for spending this time here. I know there are many places your attention could have gone, and I do not take your presence lightly. If this long journey through Webb, early galaxies, black holes, dark matter, and dark energy gave you something worth keeping, then I am very grateful you stayed with it until the end. I hope tonight brings you rest. I hope your mind can set these distant galaxies down for a while now, and let the universe keep unfolding on its own. Sleep well, Take care of yourself, and thank you, truly, for being here.